Welcome to the CSE 230 Computer Organization course. My name's Sean. I'm a TA for the lab. I'll be helping to proctor for that. I am currently an undergraduate student, as the rest of you are most likely, and I've developed a bit of videos here to help you get used to VHDL, which is a hardware abstraction language that should help you to develop your project as you go through the semester. But before we begin, let's discuss a little bit about what VHDL is and what it can do for you. So, VHDL. What is it and what's it good for? Well, VHDL stands for VHSIC HDL. What on earth is that? It's an acronym within an acronym, and it stands for Very High Speed Integrated Circuit. Circuit for those who can spell. Hardware Description Language. And what does that mean? How is it different from a normal programming language? Well, VHDL looks like a typical programming language, but it's not. It works a little bit differently, and there's some foundational differences between what a traditional programming language can do and what VHDL will do for you. But we'll discuss this more in depth as we go along. For the moment, what you can think about VHDL as is it allows you to design an object solely in a traditional, somewhat programming sense, and then you can compile this onto a chip. And what is that chip? Well, you'll see it in the lab, and it's what this thing in the background is here. This is Quartus 2. And Quartus 2 allows us to compile designs for the Altera family of FPGAs, or fully programmable gate array chips. And these chips are customizable via software download, so that you can demo or model pretty much anything that you want to on them within reason. So for instance, if I have an FPGA chip, I could put a simple stopwatch on it, or I could put an MP3 player on it. You know, it all comes down to what I've designed for it and what I can use it for. In your case, you'll be building a processor on it that'll do some simple processes like addition, subtraction, XOR, and whatnot, and so forth. So let's take a look at the Quartus 2 IDE right here. We've got a basic, this is what it'll look like when you come into it. This is actually the student version, version 9.1. It's fully downloadable off of Quartus's website. So let's start a new project. We'll just go to new here, and that wants us to do new files. So we'll go to new project wizard. And this just tells us basic info. We're going to need to know where we want to create it, and I've created a folder there. We'll have to name it something, so we'll call this simple project. And we'll hit next. And then it'll ask us if we want to include any files in the project. We don't have any pre-made files, so we don't have to worry about this. If you have pre-made files later on, this is where you would include them. We'll hit next. Here's where you can choose which piece of equipment that you want to use this for. So throughout here you see all these different chips that Altera provides, and in fact there's different types of boards that Altera provides here. We'll be using a Cyclone 2, and it'll be one of the chips underneath here, but for now we don't need to care about which device we're using, so we're going to take auto device selected by the fitter. This allows us just to play around without having to worry about how much memory we have and how much we're going to run out of. So we'll hit next. We don't need to worry about any of the EDA tools, and it'll give us a basic readout of what we've done so far and what it's going to create. We'll just hit finish. Okay, so we've got nothing now. Completely blank. Yay! Okay, so let's start working here. We'll go to File, New, and we're going to create a block diagram schematic file. It's here underneath Design Files. It's just in this drop-down. And that gives us this right here. And this is basically, think of it as an architect's design for computers, or for our FPGA. And this allows us to put down all of our different models that we'll develop, either in VHDL or in schematic capture. Right now we're playing around in schematic capture, which truly allows us just to draw right on it. So let's start some drawings. Over here is our toolbar, and our toolbar allows us to select different items that we'll use within our schematics. So right here we'll scroll down to Symbol Tool, and underneath Libraries, we can see all these different items right here. Mega functions are something that we will use later on, but for now we're not going to care about. We're going to come to Others is another field that you usually won't have to worry about, but right here is our meat and bones. This is primitives, and underneath here we have all the traditional things that you might want in a design. So for our case, we want some logic. Let's build an AND gate. Okay, select it, and we'll just left click anywhere we want, and we have an AND gate. Sometimes Quartus's IDE is a little bit wonky, as you can see here, this yellow line overlapping this blue. If that happens, just click on it or drag it around a little and it'll clean right up. So an AND gate by itself isn't too terribly interesting. Let's grab something else. Let's grab an OR gate. Right here you can see we have all these different gates that we can choose from. This is binary, not another B OR gate right here. We have a couple NAND gates here, and we want the 2 OR gate. We're going to plop that down right there in front of our AND gate. A little bit more. Okay, so now we have 2 gates, but they're just kind of floating in space there. Is there any way that we can connect them up? Definitely. So right here we come to our orthogonal node tool, which is really just a fancy way of saying wire. So we're going to grab this, draw a wire here, and then we're going to draw a couple more wires floating out in space right here. One here, and another one down here. One more right out here. Okay, so now we have some wires and we have some gates, but we're not really doing anything with them. So let's grab our tool again. Only this time we're going to scroll down to pin. This is what allows you to connect up to the different controls on the VHDL, on the chip for Altera, and would also allow you to do simulations within Quartus here. So we're going to grab an input, and if I just click again, I can put another one down and another one. And then we also want to grab an output pin. It's nice to have things that do stuff, right? That's exactly what the output's for. So now we're just going to connect them up. Make sure it turns into a box when you drag it all the way over. Otherwise, most likely you're not actually making a connection. If you don't make a connection, you'll see a little X where your line is. Having these names here, pin name 2, pin name 3, isn't exactly very interesting, so let's rename that. We're going to double click here where it says pin name, and we're going to change it, so I will call this A in, because I like to have a convention that lets me know what an input is. B in, we'll call this C in. And this guy over here, I'll just call result. Okay, awesome. So now we've made a block diagram of a very simple function here. Alright, let's save it. We'll just call it simple project. And then we're going to go make it go. So up here in this toolbar along here, you see this little button right here, Start Compilation. This will go through the full shebang. If you hit this button, it'll compile it, it'll design it for what it needs to do for the board, and you will be able to upload it straight to the board. That can take a little bit longer, so for our purposes, we don't need to do all that. We're just going to do the analysis and synthesis, which goes through all the compilation, but none of the necessary fitting and plotting for the chip specific. So we're just going to click that. You'll start to see over here, there's a percentage bars that goes through each one of the steps, and hey, I didn't mess up, so that's a step in the right direction. Okay, so now we can see here that the total number of logic elements it used, the functions that it implemented, and the total number of pins. Down here you get a little bit more information that you may want. Sometimes you get info, sometimes you'll get warnings, and then worst of all is obviously the errors. We have none of those because we are all awesome programmers who never make mistakes. Okay, so that's great. So now we have a compiled design, but what can we do with it? Well, we want to simulate that. So we'll come up here to File, we're going to go to New, and we're going to go down to Vector Waveform File. That's underneath Verification and Debugging Files. That's going to be what allows us to see how this function behaves over time. So we're going to say OK, and that gives us something here. Right here underneath Name, if you right-click, you can go to Insert, and it'll say Node or Bus, and we'll go to Node Finder, and then right up here where it says Pins All, that's exactly what we want, and we're going to list them. This lists everything that's on that design. So we're going to say we want A, we want B, we want C, and I'm going to hold down Shift. There we go, we want everything. Alright, it's going to say multiple items. We have a different radix that we can sort here. So if you have what's called a multi-vector bus, in other words, if you have multiple bits on the same line, it'll give you the option of seeing it in ASCII, in binary, in hexadecimal, octal, signed, unsigned, all that fun stuff. We really don't need to worry about what we're doing here, so we'll just leave it in hex. Our bus width is 1, just means we're 1 bit wide. We'll say OK. So right here we have these are all of our inputs, and then our result is an output, and it lists all these little hashes right here because we don't have anything going to it. So we need to put some inputs on our different lines here. We're going to take this and right click and go to Insert, or excuse me, we're going to go to Value, and we're going to go to Clock. Clock allows you just to turn it from high to low, high to low, high to low. There's all different options in there, including ones that are arbitrary or completely on or completely off that you can play around with. So we're going to make this kind of quick. We're going to say that it's a 5 nanosecond period with a duty cycle of 50%, so it's a square wave. And there we go. We're going to do the same thing for B, clock, except we're going to double him. And we're going to do the same thing for C and double him again. 20. And there we go. Those are going to be the different values that get simulated on this result. So we're going to save this here. It'll ask you for a name. We'll call this simple project waveform. And now we can simulate. So we're going to go to processing and start simulation, or you can go to simulator tool. I prefer the simulator tool. There's two different modes of simulation. One is timing and one is functional. Functional just simulates the exact results. So if I have A and B together, it will give you a C, or however we define our function. Timing gate delays, and gate delay is when I turn the power onto something, it takes a little while to push through that device. Now I grant you we're talking electricity here, so this isn't very fast, or excuse me, very slow. This happens on the order of nanoseconds, but for our simulations, nanoseconds matter, and you'll see as you work on your project that certain things will start to delay how long it takes to get through your system. So the more components you have in your path, the longer it's going to take. That's what the timing analysis will tell you, and it'll be really instrumental in helping you to discover timing issues that are going on in your circuit. For instance, something's happening on this part of the circuit, but it needs to be to a different part faster, so you can kind of fine-tune that. But for now, we're just going to do functional. We don't care about any of that timing stuff. In order to do functional, you also have to generate this functional simulation netlist. So we'll hit that button. It'll do some magic here while we're waiting. It's successful, and then we can just hit start. Oh, excuse me. You also have to input a file. Now we'll start. Simulator successful, and we can go down here to report and view. That looks like a mess, so what we can do is grab our little zoom tool over here and we can start zooming in to figure out what is going on. So as we can see here, when A and B are both high, it's true. Or anytime when C is high, it's true. And when they're all false, it's false. So we verified that our function works. That's pretty cool. But for large projects, it's going to be kind of a pain in the butt. You don't want to be sitting there drawing a million AND gates or a million OR gates over and over and over. Even with copy and paste, that gets a little bit tedious. So what can we do to save a little bit of our time and, if we're lucky, a little bit of our sanity? Well, that's where VHDL comes in. So I'm going to close this project and we're going to open a new one. Actually, I'm going to scratch that. I'm going to reopen that project because we can do it right in here. So let's implement this entire function here as a single VHDL file. It'll save us some time. We're going to go to New. We're going to go to VHDL file here. That's underneath Design Files, once again, just like our block diagram was. And here we go, a blank sheet of paper. Holy God, what do we do with this? Well, we're going to start doing what we're used to doing, and that's filling it up with words that make some sort of sense for the computer. So we're going to start by saying library. Library is just a standard set of functions. Quartus comes with a couple of them. The big one is IEEE. This has standard definitions for things like logic vectors for buses and sometimes some math functions as well that you might want to use. And we need to use this library, so we're going to say use IEEE standard logic 1164, which defines a bunch of different variable types, all, because we want everything. Now we need to create our entity. Well, let's name it entity. This is the basic definition for any object in VHDL. So we're going to call ours simple object. And our simple object is an object with a port. What's a port? Well, a port is these guys right here. It's our A, B, and C, and it's going to be our output. It's basically all of the lines going in and going out of a project. So we're going to have an A, a B, and a C. And all of these are going in. and they're going to be standard logic vectors, and that just means that they have 1, 0, and a couple of other special ones like high impedance, low impedance that you don't have to worry about for now, but they're there in case you start needing to worry about them for later. We're going to make one more. We're going to have a result, and he's going to be an output. And again, standard logic, because it helps to have things that match up. You can do it without matching them up, but it gets a little bit messy. One note there, I just deleted the semicolon at the end of standard logic. VHDL needs that in order to do the port. It actually has it right here. So that's one kind of weird programming construct that you need to wrap your head around. Finally, now that we've defined what our simple object is going to be, we're going to end it. So we're going to end simple object. Okay. Now let's save our simple object. We'll save him as, and this is something that you'll also need to notice, we're going to call him simple object VHDL. The name of the file must match what the entity name is. Otherwise, Quartus will throw a fit, it won't compile, and you'll spend hours beating your head mercilessly against the computer wondering why it doesn't work. Not that any of us have done that. Alright, so now we have a simple object, but we probably want to make it do something here. So let's define what it does. In order to do that, we need to create what's called an architecture for it. We do that by using the architecture keyword. So the architecture, and you can call it whatever you want here. So we could call it foo, I like to call it behavior, because that's what we're modeling here. We're modeling the behavior of our simple object. So the behavior of our simple object is, and now we must begin in all bold. Caps actually doesn't matter in this. Be sure that your variables are all named differently. It is not case sensitive, it will not pay attention to that. But we want to just put that same function onto a result line again. So here we go. We're going to say result is assigned A and B, which was our AND gate right here, or C. So we have the output of A and B, which would be this line right here, getting ORed with C coming along here. And that goes to our result. So now we just put a semicolon there and say end behavior. That's it. Pretty simple, huh? So now we're just going to save it once more, and we're going to compile it. In order to compile it, there's a couple of different methods. There's a button on the drop down on the side here. Should be this guy, analyze, or you can try to compile him from up here again. In order to do that, there's a little trick in Quartus that you have to notice, and we'll come over here to simple object, and you left click on him, and then you'll right click set as top level entity. Anytime you hit compile over here, it only compiles what it considers the top level entity and anything that's necessary to make that top level entity. So if your project does not include our simple object, it won't do anything. So for our purposes, we want to make him the top level entity, and then we're going to hit start analysis and synthesis. Once again, it'll compile. It's saying, oh God, I'm a horrible programmer, I should give up now. And now we can do some analyzation here. So the architecture behavior is expecting a line here, and that's right here that I forgot a semicolon. So we fixed it, and now we'll start our analysis and synthesis once again. Yes, we want to save. And there we go. No more embarrassing lacks of semicolons for this programmer. Okay, that's great and all. So now we've compiled it once again, but what can we do with it? Well, let's say that we want to drop it onto our schematic here. We want to have a function that does something cool. And we might want to tie it into some of our lines that we've already written down here. Like, I might want this A, B, and C to hook up to that file that I just made. So let's go back to it. We're going to go to File, and we're going to go to Create/Update. We're going to go down to Symbol Files for Current File right here. It's going to do a little more compilation once again. It's going to say it was successful, and that's awesome. So we're going to come back to our project here, and we're going to go once again to the Symbol tool. We click on him, and now there's this little project box right here. And that project box has our simple object. But if it wasn't in there, for instance, if someone just gave you a VHDL file, you can just go here and browse through anything that you want to browse through again. So we're going to grab him, we're going to say OK, and we are going to put him right here. So that looks pretty spiffy, huh? A nice little object that has just 3 lines to it and a result. So let's hook it up to some stuff. And in fact, let's hook it up to the exact same things that we have running into our gates. So we're going to hook up our A line and our B line and our C line. And I'm just going to copy and paste. And now I have another pin for result that I can rename to VHDL result. So now we can compare the two of them and see if the functions are the same. And we'll connect him up. We'll save and compile. Everything's good to go. So now we can come back to our vector waveform file, which is right here. And we can go once again to Insert, Node or Bus. We're going to find the nodes again, list all of them. And it didn't find it. Which is odd. So, give me just a second here. We have our output. We will compile him fully. And once again, we have warnings here. This is saying that we don't have a license and we have unused pins. So, result has no output capacitance. That's quite alright for us. So hopefully our vector waveform file will find it this time. So once again, we'll come into here, insert node or bus, node finder, list. Oh, excuse me, I know why this is doing it. Again, it caught me. So because I compiled that and this wasn't the top level property, top level entity, it was compiling our simple object VHD. So we'll go back to him, make him the top level, and try again. And I will apologize for wasting a minute and a half of your time on that. Okay, so now we're good to go. We'll come back once again into our waveform, insert node or bus, find the node, list everything. Haha, there we go. Click on him and put him into the result. Okay, so we'll save. And we'll come back over here to our simulator tool. We have to generate a netlist again. It's successful. And we will start once more. Simulation's done, and report. So yay, here we go. We can see that the result, which is the one that we drew by hand, is the exact same thing as the VHDL. And we can scroll through and see that it's going to do the same thing over and over and over until the end of time. So we're successful. So that's two ways of looking at a project, essentially. What you have here is a schematic capture version, which allows you to draw things in by hand, which can be very handy for connecting up objects that you've designed internally. For instance, if I have a bunch of these little VHDL objects, I want to wire them up, I can just copy and paste them all over my diagram. And all I have to do afterwards is just wire up where I want them to go and what I want them to do. But for the internals, some of these guys are great to do in VHDL because instead of wiring things up by hand and clicking and dragging objects around the screen all day until your eyes bleed, you can just write a little bit of code right here. So we can copy and paste this and reuse this code over and over and over. So I hope this helps you to see a little bit of the versatility of VHDL, and in the future episodes of this we'll go into a little bit more of the interesting things that we can do with VHDL, and we'll start to show you some of the magic behind it. So if you have any questions, comments, or concerns, you can email me. Otherwise, I'll see you in labs on Thursday. Thanks for listening.